So I just wanted to do one exercise on infinite time horizon, or one sort of example where we just essentially just use what we've just proven, is that if I can solve the Bellman equation for some policy, then I've essentially solved the problem. I've got the optimal answer. Okay, so let's do it for this one. And like I say, I like to kind of do gambling examples and things like this. Let's just check that's working. Can everyone read that okay? Is it too light? So it's a bit too light over here. So I can turn maybe the middle light off or something like that, and then it'll be a little bit better maybe. Okay. It isn't any quieter here than the other room, is it? Okay. So let's have a look at this. So we've got a gambler has I pounds. Okay, so he's got a certain amount of money, and he wants to win. He wants to win N pounds. Okay, he wants to have a certain amount of money. Thanks. The gambler can bet any amount of money J less than the money that they've got I. Okay, so you've got some money. Let's say it's £5. You want to make £100, and you can bet anywhere between. You can bet 1, 2, 3, 4, or £5 if you've got £5. Okay, right. We'll assume you have to bet something. Okay. The gambler wins that specific bet that he makes at that time with probability P, or loses with probability Q. And if he wins, he gets his money back, and then the additional amount of money. So if he bets £5 and he wins, he gets his £5 back, and then plus another £5. Okay? And if he loses the £5. Okay? Does that make sense? Okay? Okay, and the game ends when either the gambler's lost all his money and got £0, or there's got N pounds. Okay? And for this question, we're going to assume that the probability of winning is bigger than a half. Okay? And the exercise, or what's been asked here, is to argue that it's always optimal for the gambler to gamble £1. Okay? Okay? So you basically gamble the minimum amount of money that you can gamble at each time. Okay? All right? Does everyone understand the question? Okay, so it's not worth, if you've got £5, the chances of winning are positive, then you should bet small but many times. Okay? You should note that that kind of intuitively makes sense, because the bigger I gamble, the more variance, or the more sort of randomness there is in the outcome. Whereas if I make a smaller gamble, then the variance is smaller. Okay, so you can kind of think of things as the strong law of large numbers, saying that I'm not going to be oscillating around too much if I make small bets, and it's just going to steadily drift up to the amount that's winning. Okay, of course we've got to prove that actually that intuition makes sense. Okay, all right. Okay, so let's answer this question. Okay, so again, if I was to ask you this as a question in an exam or something like this, I'd probably break it down into smaller steps. So when I give you an exercise like this, what's the first thing I generally want you guys to do? Got a question. It's about a dynamic program Markov decision process. Okay, I have to find it. So what do I usually want you to do? Yeah, I think, say it louder. Yeah, write down the Bellman equation. Okay, so always write down the Bellman equation. It's always useful. Okay. So we're going to let V be the optimal value, okay, from being in state I. Okay. Now the two specific states, what is the value of being in state 0 in this example? So having no pounds, you've got no money left to bet, so 0. Okay? And we can assume that the value, okay, of being, say, in N is worth, we'll say 1. It could be n if you wanted as well. We'll just say 1. It's like 1 for winning, 0 for losing. Okay? We can multiply everything by n and be n for winning, 0 for losing. Okay? Right. Okay. So in Bellman's equation, I maximize over the sets of actions I can take. Okay? And the sets of actions you can take are the amount of money you can bet. So you can bet if you've got I pounds, you can bet 1, 2, 3, 4, 5, 6, all the way up to I. Okay? So the sets of actions that I can take, J, which I said is the amount that you bet here, okay, belongs to the set 1 up to I. So I can either bet £1 or I can bet all my money or anything in between. Okay? Okay, and then we have to look at if I've got if I make a bet of size J, there's two things that can happen. So first of all, in Bellman's equation I write down it's the instantaneous reward plus the expected reward from the next step. Okay? So what is the instantaneous reward if I'm at some state I, which is not equal to 0 or n? Do I get any money? So I only get a reward at the end, okay? But I don't get any rewards in between until I reach either state 0 or state n, okay? There's no instantaneous reward. There's no reward for the action that I take until the very end of the episode, till the very end of the gambling session, okay? You've either made lots of money, or you've lost everything, okay? Okay. So there's no instantaneous reward. So like little x of a here is equal to 0, really. We only get a reward at the very end from these guys, okay? All right. So with probability P, I win, okay? And then how much money do I have? Yeah, so I think someone said it correct over there. So I win I plus J, okay? With probability P, okay, I get to the new state I plus J, okay? So I get my money back, and then I get an additional J pounds, okay? With probability Q, okay, I lose J pounds, okay? So I go to a state with, I minus J here. And that's it. Okay, that's the Bellman equation for this problem. All right? So notice really this is just so really what I've said here, and just to kind of spell it out a little bit more, is that if I look at this as sort of R of X of A plus E of V of X hat, given my bet J, this is that term, and I said that this one is equal to 0. Okay? Okay, so that expectation expands out with probability P, I go to this state, that's my X hat. With probability Q, I go to that state, that's my X hat, depending on which happens. Okay? Okay. So it says to show that it's always optimal to bet £1. So we're going to let R of I be the reward if I always bet £1. Okay. Okay. Okay, and I can write down the recursion that that satisfies. The reward that I get from I is equal to, with probability P, I go to I minus 1, and with probability 1 minus P, or Q, I go to R of I plus 1. Okay? Now this is a kind of, it's like sometimes called a second order difference equation. It's an equation you can solve, basically. I can give you a hint in a minute as how you solve it. It doesn't really matter too much. But you can show that the solution to that equation is 1 minus q over p to the I divided by 1 minus q over p to the n. Okay? I'll briefly give you a hint as to how you go about solving that, or just, it's not really too important why, but notice that I could write here that R of I is equal to P R of I plus Q R of I, okay? So then I end up with this equation that P R of I plus Q R of I is equal to P R of I minus 1 plus Q R of I plus 1. Okay? And then I can collect the two sides of this together. Okay? Then I get that Q R of I plus 1 minus R of I is equal to P R of I minus R of I minus 1. Okay? And now I've got something that's not too bad. It looks just a bit, it looks messy, but if I called that U of I plus 1 and I called that U of I, okay? I call that U of I, and I've got Q of U of I plus 1 equals P of U of I. Okay? And now I can solve for U really easily. And then from U, I can get R, and that'll give me this. Because notice, I can just notice that it decreases geometrically. These U of I's have to decrease geometrically. Okay? Because Q of I plus 1 is equal to P divided by Q of U of I. And then to have that is equal to P divided by Q squared, U of I minus 1. And I keep on going all the way down to 0. Okay? Anyway, that's there if you want to think about how to solve it, but it's not too important for this class. If I come up with an equation like this, I'll kind of tell you what the solution is, or give you a very big hint how to solve it. Okay? Anyway, so I've got my Bellman equation here. I've got a value function, or the reward function associated with betting £1 always. Okay? And I'm in a situation where I want to apply my theorem. It's a positive program. Okay? So I want to apply this theorem over here. I've written this down. I've solved what R is. Okay? So now what I need to do is check that R actually solves the Bellman equation. And if it does, then it has to be the optimal value function. Okay? So now what I do is I take that function R and just check that it satisfies Bellman's equation. All right? So let's just check it. We can just check it. Okay. So essentially what I need to happen, so to apply theorem 1, we need to check that R of X satisfies Bellman's equation. Okay. So what I need is that if I put in this r into this equation, then it's going to give me the right answer. That r of I is equal to the maximum over j between 1 and I of this expression here. Okay? So we check that 1 minus q over p of I is equal to the max of j equal 1 to I of p of 1 minus p over q of I plus j. Okay. So notice this is the first term from here, and this is the I plus j term from here, times p, plus q, 1 minus q over p, I minus j. Okay. Right. So we need to check that the maximum of this expression here is equal to the term when I take j equal to 1. Okay, you can notice if I put in j equal to 1 here, the maximum term is going to give me that. Okay, so how do I check that? Well, you can, I'll let you do this in the comfort of your own homes. You can check that as I change the values of j in here, if I let j get bigger, then this expression is going to get smaller. All right? So if I let j go to 2, go to 3, all the way up to I, the term inside this bracket is going to get smaller and smaller and smaller. Okay? So in particular, you can check that f of j, which is equal to minus p q over p to the j minus q over p to the minus j is decreasing in j. So that's just this term and this term here. Okay. Oh, and I should be careful, that should be multiplied by q. And you can do that with calculus. You just differentiate it and check that the derivatives are negative. Okay? So all you need to do is just differentiate that with respect to j. Okay? And notice that that function is decreasing. As I let j get bigger, the derivative is negative, so it goes down and down and down. Okay? So the maximizing value is when j is equal to 1, okay? Which is exactly the expression over here. All right? So now you say that, so you can say that so R of I above satisfies the Bellman equation so by theorem 1 R of I is optimal. Okay. So that's the basic structure of how you go about applying that theorem. Okay. You write down Bellman's equation, and then you think, what is the reward function that I get from my policy? And you check that that satisfies Bellman equation. And then, in your exam script, you state by theorem 1, or by theorem 2 if it's a negative program, okay, that policy must be optimal, okay? So just to track back a little bit, I'll let everyone, has everyone written that down okay? That's all right? So there's two things to check. This argument here you can check, and this part you can check. If you've got any issues with that or problems, do ask me at the tutorial. We'll do the next tutorial class, okay? So it's kind of interesting that if the odds are in your favour, okay, then it makes sense to bet as small as possible, okay? Because every time you bet, you're taking on the least amount of risk, okay? And so if you think of like the strong law of large numbers, it's just going to drift you up towards n, towards the maximum reward. In fact, you know, if you could bet in pennies rather than pounds, you'd bet 1 penny all the time. It just you'd be taking such a small amount of risk, there'd be such a small variation about that it would eventually just slowly drift up. Okay. Now let's think about it the other way round. Okay. Let's suppose that the odds are against you. Okay. Let's suppose that your chances of winning, P here, are less than a half. What do you think might happen then? What do you think the optimal policy would be? So let's think if you betted small, would that be a good thing? Well, no, because it's just going to do exactly the same thing but in the opposite direction. It's just going to sort of, you're taking on the least amount of variability, and it's just going to slowly drift you down towards 0. Okay? So given that betting the least amount is not the right thing to do, what do you think the right thing to do is? Yeah, bet as high as possible, yeah? So if the odds are stacked against you and you're trying to reach a specific target, okay, then the best thing to do is bet the maximum amount. You basically go like, okay, I need to make £1,000 and I've got £5, so I bet £5 and I get 10. And I bet £10 and I get 20. I bet £20 and I get 40, and you just keep on doubling up till the maximum answer, okay? Another thing to think about with this question is like, what if you wanted to, if you didn't care about the losing? What if you had a lot of money and the chance of you going down to 0 is basically not possible, that you just need to hit above an amount, okay? So one of the things you can do is you can, if for any betting problem, you can always win £1, should we say, okay? So what you can do, this is called like a doubling strategy, okay? So let's suppose I've got £0 and I can bet any amount I like, and I want to make £1, okay? And let's say, for the sake of argument's use, I've got a 50-50 chance of winning. It doesn't actually matter if it's 50-50 or whatever, 2/3, 1/3 or whatever. Okay, so you make a bet of £1, okay? If with 50% probability you go to £1, because you've won, and with 50% probability you go to minus £1, okay? So then, you've got to make £2, okay? So what do? Well, you bet £2, okay? If you win, you go up to having a total of £1. And if you lose, okay, then you go down to minus £3, and you need to make 4. Okay? So the next round, you bet £4. Okay? And with probability a half, you go up to £1. With probability a half, you go down to minus £7. Okay? And then you've got to make £8. So then you bet £8, and you just keep on going. And eventually, you're going to win, aren't you? Okay? And you'll end up with £1. Okay? So you can always win £1 from any betting game. And obviously, you can make £1, you can always make £2, and so forth. Okay? So does anyone see like an issue with that? So in fact, there kind of isn't any issue with that. But notice that that's a perfectly valid betting scheme, and you can always make money doing that. Okay. The only problem is that the amount of money that you need to keep playing this game doubles at each round. Okay. So you essentially have to have more money than the casino that you're betting with in order to win this way. Okay. So because you need to double your amount of money, and you can imagine it's going to take a while, and you're going to need a lot of cash in order to get that £1 out. Okay. So one of the interesting things is that this is something that, in some sense, like recently, I think the last year or so, there are a number of like high stakes casinos in London that went bust. Okay, and that's sort of because of this phenomenon. Essentially, what happens is these rich billionaires come into London, and these casinos, they have like an amount of money, a few hundred million, or maybe like 100 million or 50 million or something like that. Okay. And these people are so much richer than the casino that they can essentially, effectively apply a doubling strategy and always beat the casino, if you see what I mean. Because they can just keep on betting, and the casino runs out of money in order to keep up with them. And so, these kind of principles, they kind of apply. Okay. All right. Anyway, so I'm not sure how much more we'll do about betting. I can do about things, if I get time later, we'll do things about like how to optimally play blackjack and things like that if we get the chance. Okay. Okay. So anyway, so that's some of the stuff on infinite time horizon. Okay. So now I want to go about methods for solving Markov decision processes. So if we've got an infinite time Markov decision process, here I've just kind of stated what the answer is, and you've just kind of checked it. We actually want to go through some sort of procedure to optimize a Markov decision process. Okay.